So, where? Sorry.
The first question of number theory.
On number theory, okay. Is that okay with you guys? Do you want to start with number theory?
Are you doing all of it though?
I can if you want.
Yeah.
Do you want me to just go through the whole thing, just like each section? Yeah, it's on a different, we have like a separate WordPress for Study Union, and I posted it on there. I should have posted it on my normal one too, but I didn't. So, UCF, Study Union, and under Computer Science, it's like right here. Huh? Sure, yeah. Okay. Thank you. Okay, can you hear me? Okay, so I guess we'll just start with logic then. Is that okay with you guys? Okay, cool. So, hi. The first one is use the laws of logic and rules of inference to prove the following logical argument. So the premises are P implies Q or R implies S, not S implies not Q, and P. And our conclusion is S. So the first thing I like to do is just label all the premises. Oops, that should be 2, 3, and 4. And then just write premise for all of those. And I'm going to pull up the reference sheet that he gives us. I have it bookmarked right here. And so then we can use these to solve the problem. And the first thing I see is that we have P right here, and then we have P implies Q or R. So we can write for step 5, Q, sorry, that's an OR, Q or R. And that would be modus ponens right here. So modus ponens with 1 and 4. And then after that, we can flip this one around using contrapositive. So that would be Q implies S, and that would be contrapositive right here. So contrapositive with 3. And sorry. Now we have R implies S and Q implies S. And I gotta find which rule that is, but it's, let's see. Yeah, thank you. So, wait, no, it's not that one. It is, yeah, you're right. It's rule for proof by cases. So this one states P implies R and Q implies R, implies Q, or P or Q implies R. So for this one we would write, sorry, yeah, Q or R implies S, and that would be proof by cases with 2 and 6. And now the last thing we have to do is, because we already have Q and R proved true, we can just write S, and that's modus ponens again. With 5 and 7. So that's all we have for that problem. Does anyone have any questions about what we did for that? Or no? Yes? Yeah. We have not S implies not Q. So with contrapositive, we can flip them around and switch the signs, which is what it says right here. So that's all we did for that one. It would really be like not Q, but we kind of like skipped the double negation step. But yeah. Any other questions? If not, I'll move on to the second one. And I'm going to pull up my thing again. Okay. Number 2 is the same thing, basically. Our premises are R and not S, or Q and not S. Not S, sorry, implies P and R implies U. Then we have U implies S and not T. So same thing again, we're just going to label our premises. Sorry, I forgot our conclusion, which is P implies Q. So, well, this is just premise, and premise again. And the first thing I would do is, you see how we have R and not S or Q and not S? We can use the distributive law right here, and we can use that to like rewrite that. So we would get not S and R or Q, and that would be distributive with 1. And then after that, we can split these up basically using conjunctive simplification. Since these both have to be true, we can write them separately as true. So not S, and that'd be conjunctive simplification with 4. And that one, here it is, right here. And we can do the same thing with the other half, R or Q. Sorry, that's conjunctive simplification again. And next, what I would do is, you see this premise right here, U implies S and not T. Since we have not S to be true, that means that this like little group is false. So using modus tollens, we can write not U, and that would be modus tollens with 3 and 5. And we can also use modus ponens with not S to write this one. So that would be P and R implies U, so that's modus ponens with 2 and 5. And then this also will use modus tollens again. So it would be not P or R and 8. So then we can do De Morgan's. So not P or not R. That's De Morgan's. And that one is up here, this law, with 9. And then after that, let's see, up here we have, let's see, what did I do next? Okay. You see how we have this one and this one, and it's got R and then not R. Using the rule of resolution right here, we can simplify that to not P or Q. And that would be resolution with 6 and 10. And now this one is just our rule of implication, or implication identity right here. So not P or Q, that can be rewritten as P implies Q. And that's the end of that one. So implication with 11. Okay, does anyone have any questions about that one? It's a little bit longer than the first one, so. Yes.
I missed it, but where did the rule of resolution come from?
It's one of our rules of inference right here, number 13, which basically says if you have P and Q or not P and R, you can simplify that to Q or R. Does anyone else have any questions? I'll post all the solutions, by the way, right after the thing. If no one has any more questions, we can move on to the next section, which is sets. Our first question is prove or disprove the following statement. Basically, it says if A is a subset of not the intersection of B and C, that implies that either A union B is empty or A intersection C is empty. And like for this type of problem, we can disprove this statement using like an example. So I'm going to say that this statement is false. And my example would be if A equals 1 and 0, then and B equals 1. Sorry, that's a weird symbol. And C equals 0. Then B intersection C, that would be empty. And then that would make A not a subset of the intersection. But if we take the union of A and B, we'll obviously get 1 and 0 because those are all like the common elements of that, Then A intersection C would be equal to 0. So like A is not a subset of B union C, but A union B does not equal the empty set. And A intersection C also does not equal the empty set. So that's all we have to do for like these types of problems. Yes?
The question states that A is a subset of not the intersection C.
Yes. That's another way of saying that A is not a subset of that. So like not B intersection C, that's basically all elements that are not common to both sets. So that would include elements that are unique to each set. So in this case, that would be 1 and 0. Because they don't have any elements in common, their intersection is 0 or is empty. So that would just say that A is a subset of all the elements that are unique to both sets.
Okay.
Yeah. I think that is like the trickiest part of this question, is trying to figure out like what exactly they're saying, because it looks really creepy, right, with all the symbols and stuff. but yeah. If you were to counter this type of problem and you weren't sure whether or not it was true or false, I think the easiest thing to do would come up with like a small like example like this and see if you could find an example that doesn't prove that. And then that's all you need for this. Like, this is literally the whole answer. Does anyone else have any questions? Yes. Mm-hmm. Yeah. You would have to like make like an arbitrary like general case because like proving a for all statement, you can't just come up with like one example. So like a Venn diagram also wouldn't be like necessarily like wouldn't necessarily include like all the cases. You'd have to like assign arbitrary values of each thing and then prove whether or not like this value is a subset of everything or whatever. That would be a much harder question, I think. Any other questions? No? I'll move on to number theory then. Okay. The first question is finding the GCD of 2n plus 1 and 3n plus 2. And that one we can just like do like a kind of like weird Euclid's algorithm. So we could say 3n plus 2 equals 1 times 2n plus 1 plus n plus 1. Because if you like were to add these together, you get 3n plus 2. And then 2n plus 1 equals 1 times n plus 1 plus n. And then n plus 1 equals 1 times n plus 1. And then n equals n times 1 plus 0. So that would mean our greatest common divisor between the two of them is just 1. So GCD 2n plus 1, 3n plus 2 equals 1. And that's it. Do you guys have any questions about this problem? I thought it was kind of cool because it wasn't like just a number, you know. But yeah.
I was trying to multiply it by like x and y. So I don't know if that's right. So you could literally like just use x instead of like differentiating them. Right? Don't we have to use x and y?
No.
No.
Mm-mm.
Okay.
For a question like this one, we would use x and y, but there's no x and y in this problem anywhere. It's just like running Euclid's algorithm on like these two like non-specific numbers or whatever. Any other questions? Okay. Our next problem is find all integer solutions to 189x plus 73y equals 1. And we would just run Euclid's algorithm on that. 1 second. Here. Okay. So 189 equals 2 times 73 plus 43. 73 equals, let me move all this over. Okay. 73 equals 1 times 43 plus 30. 43 equals 1 times 30 plus 13. 30 equals 2 times 13 plus 4. 13 equals 3 times 4 plus 1. And then we would rewrite all of those. So okay. And then for the extended Euclid's algorithm, we would write 1 equals 13 minus 3 times 30 minus 2 times, whoa, times 13. And then that equals negative 3 times 30 plus 3 times 13. Hi. And then that equals negative 3 times 30 plus 3 times 43 minus 1 times 30. Then that equals 3 times 43 minus 6 times 30. Yeah. Okay, so once we get to this point where there's no more substitutions we can make, we would say that x1 equals 9, because that's our value multiplied by like the x coefficient, and then y1 equals negative 24. And then we would use our formula for all integer solutions. So if we have ax plus by equals c, our like formula or whatever would be the set of all x and y such that x equals x1 plus bn over c, and then y equals y1 minus an over c. Then n is an element of the integers set. So then we just plug in all our values because we have x1, we have a, we have y1, and we have c, and we have b. We have all of that. So our final answer would be the set of x and y such that x equals 9 plus 73n, and then y equals negative 24 minus 189n. C. So that's our final answer. Does anyone have any questions about that problem? Yes. Yeah. To where? Like here? Is here good? I could zoom out if you want to see the whole thing. Oh, okay. Cool. Any other questions? C would be 1. Usually it would be the greatest common divisor between A and B. So like if these are two even numbers and that was 2, then it would be 2. Or if it was one of those cases where you had to divide everything out, you would use what you got after that. Like that what would it be if you had like 2 here? So like if it was like 80 plus 40 equals 2, then you would know that like you can factor 2 out of all of that. So then you would do that and you would use 1 probably there. Or whatever they say the GCD is between the two. Yes. Yeah. Here? 2 times 13? Yeah. Oh, shoot. You're right. You're right. I did that wrong. Minus 6, right? This should be, oh geez, that changes the whole thing. Sorry. Minus 2, that would be 7. And this would be 7. This would be 7. That would be 10, right? This would be 7. This would be 10. This would be 10. This would be 17. This would be right. This should be 17. And then this should be, sorry, this should be still negative 10. Sorry. This would be 10 or 17. Then this would be 17. This will be 44, right? Okay, so negative 44, 17, 17, negative 44. Okay, I think that's correct. Yeah, sorry about that. So when I was up here, I distributed this one wrong. So I forgot that there was this -3 here, and I just took it as if it was a +2. So I changed this coefficient, and then everything down here pretty much changed because of that. So I redid it basically with the new coefficients or whatever. So then we ended up with 17 and then -44 as x1 and y1. So that just changed these down here. 1744. Okay. Any other questions? Can I move on then to the next question? Okay. So the next one we have final integer solutions, or sorry, find 87 to the -1 mod 153. That is between 0 and 53. So this one's basically the same as the first one where we run the extended Euclid algorithm, but we won't use the all integer solutions thing. So we'll start with 87 equals, 1 second. Sorry. Okay. 87 equals 1 times 53 plus 34. Then 53 equals 1 times 34 plus 19. 34 equals 1 times 19 plus 15. 15 equals sorry, I skipped one. 15 equals 3 times 4 plus 3. 4 equals 1 times 3 plus 1. So we'll stop here, and then we'll rewrite everything again. 4 minus 1 times 3. 3 equals. And we'll run the extended algorithm again. 1 equals 4 minus 1 times 15 minus 3 times 4. So we'll get -1 times 15 plus 7 times 4. Wait, no, sorry. Times 4, sorry. Then that's equal to -1 times 15 plus 4 times 19 times 15. And that'll be 4 times 19 minus 5 times 15. And times. Okay, so now that we're here, we will take this whole expression, negative 14 times 87, 1 equals, plus 23 times 53, and we'll mod this whole thing by 53. And this will disappear because mod 53 is equal to 0. So then we're left with 1 is equivalent to negative 14 times 87. And by the definition of inverse, we have like 1 is equivalent to 87 times 87 to the negative 1 mod 53. So we can write that 87 to the negative 1, which is the inverse, is equal to negative 14 mod 53. But it states in the question that we need it to be between 0 and 53. So we'll just add 53 to this one because everything that's in like an equivalent class, so everything that's equal to each other, you can like add or subtract what you're modding by, and it'll all be in the same equivalence class. So 87 inverse is equivalent to 39 mod 53. And that's our final answer.
How does that change set the range from 0 to 53?
It just means that this answer, like the answer we got from our algorithm, doesn't work. So basically it's just testing to see whether or not you know that you can add 53 to anything that's like, and you'll find something in the same equivalence class. That's all it's like testing, really.
So whenever we get a solution, a question that says that is between 0 and a number, we add the number to the value.
Yeah, and you'll get something that's within it. If it's outside of that range, if it's above it, then you'll subtract this number. That should really be 52 because 0 and 53 are in the same equivalence class. So it's meant to be like everything that's within that one like range of mod. So it should have been 52. My bad. Yeah.
So if it was 52, then you'd subtract 52 or add 52?
It would be 53. Whatever number you're modding by, that's the number that you're allowed to add and subtract with, like, and find something that's in the same equivalence class. That's all we're doing. That's like if 1 is equivalent to 5 mod 4. Like this one is just 1 plus 4. So 1 is also equivalent to 9 mod 4. That's not a 1, that's a 7, sorry. Mod 4. And we also just went that plus 4. So everything is all in like the same equivalence class when you add whatever number you're modding by. Does that make sense? Yes.
Why did 14 disappear and then come back?
What?
Like, after you modded it?
This one?
Yeah, because in the step before that, the 14 was gone.
this is just saying that, because you remember like inverse in like high school and stuff, like 3 to the negative 1 is equal to 1/3. And if you multiply 3 and 1/3, you get 1. So this rule is just saying that,
Oh, so that's not a step.
no, that's not a step. This is just definition of inverse. Yeah. Any other questions? If not, we'll move on to the next section, which is induction. So this first one is prove for all non-negative integers. So non-neg, it's n, and all x greater than 2, that the summation from n, or from 0 to n, of x to the I is less than x to the n plus 1. So our base case will be n equals 0 because it's non-negative. And the summation, the left-hand side, the summation from 0 to 0, we just plug in 0. X to the 0 equals 1. And the right-hand side, x to the 0 plus 1 equals x. And it's given to us that x is greater than 2. So we can conclude that x is also greater than 1. So since x is greater than 2, left-hand side is less than the right-hand side. So our base case holds. And we can move on to the inductive hypothesis, which is assume for an arbitrary non-negative integer n equals k, arbitrary int n equals k, that the summation from 0 to k of x to the I is less than x to the k plus I, given x is greater than 2. We'll just write that there, just as a reminder. Okay. 1 second. Sorry. Okay. Next would be our inductive step. Prove for n equals k plus 1 that the summation from I equals 0 to k plus 1 of x to the I is less than x to the k plus 2. Okay. Yes.
Or I thought for inequalities you're supposed to do proof for n equals less than or equal to.
That's strong induction, I think. When we're assuming like for all integers n less than or whatever.
Oh, okay. So that would be in the problem.
Yeah.
Okay, thank you.
That would be us like writing our hypothesis differently and stuff like that. But for this, it's just the same as normal induction. So we'll start with the summation. Sorry, that's a 0. X to the I. That is equal to the summation of from I equals 0 to k, x to the I plus x to the k plus 1. Because we just did an index shift, and to keep them equal, we have to add in the like terms that we took off, so we just took off the last term, so we have to add it back in. And then we can use our inductive hypothesis. We can write that we can like replace this one with this. So that would be k. I'm just going to rewrite it so it makes more sense visually. I equals 0 x to the I plus x to the k plus 1. That is smaller than x to the k plus 1 plus x to the k plus 1. And that is because in our hypothesis, this summation is smaller than the right side. So when we made this replacement, we got bigger. So that's why this is all still less than that. And x to the k plus 1 plus x to the k plus 1, that is equal to 2 x to the k plus 1. And back up here, we have x to the k plus 2. So x to the k plus 2, that is equal to x times x to the k plus 1. So since we're given that x is greater than 2, since x is greater than 2, we can say that 2x to the k plus 1 is less than x times x to the k plus 1. And that's it. That proves our statement. Since we're able to manipulate the left side in such a way that we can clearly see that this side, the left side, is less than the right side, that's all we have to do. Does anyone have any questions? Nope. Can I move on to the next one, or are you guys still writing? Okay.
I don't really.
Okay.
Sorry.
Yeah, it's fine.
I'm like stuck after using inductive hypothesis. So
Okay, like what we did here?
yeah, like everything after.
Okay, so let me rewrite that. So we had this, and if we look at our inductive hypothesis, we see that this summation is smaller because of the sign than x to the k plus 1. So when we replaced it, we got larger. So we can still say that like this summation is smaller than this, what we replaced it as. So that's why we have this here. And then this side is equal to this. And then we started messing with the right-hand side up here, x to the k plus 2. So x to the k plus 2 is equal to x times x to the k plus 1, right? And it was given to us in like the problem that x is greater than 2. So when we have 2 times x to the k plus 1, that is less than x times x to the k plus 1. Does that clarify? Okay. Any other questions? Nope. I'll move on to the next one then. So this one is like similar to the first one, but it's a lot trickier. Yes, sorry.
So in our last statement here, we're saying that x times x to the k plus 1 is greater than x to the k plus 1 times x to the k plus 1. So,
This one?
yeah.
What is your question?
Sorry.
Yeah.
So x to the k plus 1
Yeah.
times x to the k plus 1 isn't greater than x times x to the k plus 1?
This is just 2 times x to the k plus 1. And then this is just x times x to the k plus 1. Because like we took this from the right-hand side up here, and we just took an x off. And I guess since it's given that x is greater than 2, 2 times, it's like basically saying like if we had these, like, and we were just comparing them, we could take this off and take this off because they're the same. So 2, and then we have x, and it's given that x is greater than 2, so we can say that 2 is less than x.
But isn't there 2 of the x to the k plus 1 on the left side?
There is up here, but when we combine them, it's just 2 times x to the k plus 1. Like, if this was just x plus x, that equals 2x.
Yeah, yeah. But
So-
that wouldn't be greater than,
This, you mean? No, because x is greater than 2. So, like, if this was a coefficient, this has to be at least 3. 3 or more. Does that make sense?
yeah.
Okay. Any other questions? Okay. We'll do the next one then. So that one is prove for all integers n greater than 9 that 2 to the n is greater than n to the 3. So our base case would be n equals 10, because greater than 9 is greater than or equal to 10. It's the same thing. Sorry, that's a 10. So 2 to the 10, sorry, one second, left-hand side. 2 to the 10, that's equal to like 1024. And then right-hand side, 10 to the third is equal to 1,000. So left-hand side is greater than right-hand side. So we just put a check mark there. Our inductive hypothesis, assume for an arbitrary integer n equals k, where k is greater than 9, that 2 to the k is greater than k to the third. So our inductive step would be prove for n equals k plus 1 that 2 to the k plus 1 is greater than k plus 1 to the third. So the first thing I would do is I would factor that out, or FOIL it out, or whatever. And when we do that, we get k plus 1 to the third equals k to the third plus 3k squared plus 3k plus 1. And here's where we get kind of like more intuitive and less like concrete math. So we can say that, here, let me check my thing here, what exactly I did. Okay. Oh shoot. Basically what I did was I took this section and I assumed that this would be less than or equal to like let me think, 9k squared, because if k is 10 or greater, then these three terms, like when you add them together, will be less than or equal to this. So basically I wrote k to the third plus 9k squared, and I did that substitution again with just this section. So less than or equal to k to the third plus k to the third, because if like k is like greater than or equal to 10, then 9 times k squared will be less than or equal to k to the third, and then that's equal to 2 times k to the third. And then I use that to replace, like, with our inductive hypothesis, but backwards. So when we do that, we get this 2 times 2 to the k. And then that's just equal to 2 to the k plus 1. And that was it. This one's like a little bit more like tricky with like what we did. But all of these moves are legal if we have like this less than or equal to sign. And then once we get here, we can just do the replacement. And we have like this strictly greater than sign. And then that is equal to 2 to the k plus 1. So
How did you draw that conclusion on the last bit of the first line?
this one?
The one above that. Yeah,
This
how
one.
did we get to 9 Ks?
Well, if k is equal to 10, we have 3 times 100 plus 3 times 10 plus 1, and that's equal to 331. And 9 times k squared is equal to 900. So the greater we get, like the greater this difference will end up being. So we can just like, we could just like fudge it basically and just make that replacement. I know that's like really tricky, but yeah. And that's why we can do that. And then this is like a similar thing because we have 9 here. We know that k has to be greater than or equal to 10. So then we know that this one is also like less than or equal to that.
So theoretically, we can just make the jump to k to the third initially.
We could, but I think it would be more clear if we like did this step in between. But yeah, we could just jump to here if we wanted to.
I don't really get why you could just do that.
Yeah, I know. That's like, I don't know, that's one of like the weirdest things about discrete, I guess, is like the things we're allowed to do when we have like this sign. Like if we were just proving something equal, we would definitely not be allowed to do that. But since we are, we can like be more like adventurous maybe. I'm not sure. Sorry?
Is there any particular reason why you chose 9?
Yeah, like could you choose anything? Like that's just.
We could, but I chose 9 only because, like, because of this, basically. The n is greater than 9. Because, like, if we put 10 here, that wouldn't, like, it would still fall under it technically, but it would be, like, a little bit, like, more weird, I guess. Yeah.
So we could potentially choose anything and then just try it.
Mm-hmm. I mean, yeah. If you did anything greater than 10, though, that wouldn't always be true, so we wouldn't be able to do that. It would have to be something that's like k greater than or equal to 10. So it would have to be 10 or 9. And 9 just seems safer, basically.
So why couldn't it be like 11?
Because k could be equal to 10, and then it wouldn't be true for that. Like 11 times 10 squared, that's equal to, I forget, you know, yeah, this, right? And then 10 to the third equals 1,000. And this would be, like, that would make this statement less than this one. Yeah. Yeah. So that's why it would have to be 10 or 9.
So we're saying the k to the third plus 9k squared is less than the top one?
Yeah, if we made this 11, then this would be greater than this when k equals 10. Yeah. But since we made it 9, 10 would also be, because of the equal signs, 10 would also be like valid.
So as long as we keep it less than the original 2k plus 1?
Yeah. Yep. Any other questions? over here. Okay, I'll move on to the next one. That's this. Prove for all non-negative, sorry. All non-negative ints n that n summation I equals 0 to the I plus 1 squared equals n plus 1 to n plus 1 to n plus 3, sorry, 3 over 3. Okay, so our base case again is n equals 0. So left hand side would just be 0 plus 1 squared equals 1, and our right hand side 0 plus 1 0 plus 3 over 3 equals 3 over 3 equals 1. So these are equal. Left hand side equals right hand side. So it's been proved. And our inductive hypothesis is assume for an arbitrary non-negative int n equals k, that the summation from k, or sorry, from 0 to k of 2I plus 1 squared equals k plus 1, 2k plus 1, 2k plus 3, all over 3. And our inductive step, prove for n equals k plus 1 that k plus 1 summation 0 to whoa, oh my god. K plus 2, 2k plus 3, 2k plus 5, also over 3. Okay, so we'll do like we did with all the other ones and like mess with the summation. So k plus 1, I equals 0 to I plus 1 squared is equal to k 0 to I plus 1 squared plus 2k plus 3 squared. And now that we have that, we can replace it using our inductive hypothesis. So using IH, that is equal to, let's see, k plus 1, 2k plus 1, 2k plus 3, 3 plus 2k plus 3 squared. And now we just have to mess with this to try to make it look like this one. So we can do that by first getting this under the same denominator. So that equals k plus 1, 2k plus 1, 2k plus 3. Oh, sorry. plus 3, 2k plus 3 squared. That all over 3. So I'm going to factor out a 2k plus 3 because we have it in both sides. And I'm going to factor out this 1/3 so I don't have to keep drawing this huge line. So 2k plus 3 over 3 times k plus 1, 2k plus 1 plus 3 times 2k plus 3. Okay, now I'm going to FOIL this out. So 2k k squared plus k plus 2k plus 1. And I'm going to factor this out. 6k plus 9. 2k plus 3 over 3. And now I'm just going to combine all like terms. So we get 2k plus 3 over 3. 2k squared plus 1, 2. That would be 9, right? 9k plus 10. And now I'm going to like refactor this out basically. Whoa. And when you do that, you get 2k plus something, and then k plus something else. And if we're just messing around with it, you would see that this is equal to 2 times, let's see, 2 times 2 plus 5, right? So we would think that like the 2k would get multiplied by this 2, and then the k would get multiplied by the 5, and then 2 times 5 equals 10. So the 2 would have to be in the other one, so it would get multiplied by the 2k, and then the 5 would have to be in this one. And that would, like, if we were to redo this out, we would get 2k squared plus 4k plus 5k plus 10. And that would all simplify to this again. So that's how we would FOIL that out. So we'd get 2k plus 3, 2k plus 5, and then k plus 2, all over 3. And that matches our thing up here. So we're done. Yay. Woohoo. Any questions? Yes.
All the way to the top, when we split the summation,
Yes.
how did we get 2k plus 3 squared?
That is because when we took out the k plus 1 term, we plug k plus 1 in for I. So that would be 2 times k plus 1 squared. So you get 2k plus 2 plus 1 squared. And that equals that. But yeah. Cool. Any other questions? Okay. Well, I guess I'll move on to counting. Oh wait, no. There's one more induction one. This one is also kind of a weird one in that there's not really that much math involved. So it's basically prove for all integers n greater than or equal to 2 that a set with n elements has exactly n times n minus 1 over 2 subsets with 2 elements. So this one like looks really weird, but it is an induction one technically. So our base case would be n equals 2. So base case n equals 2. And if a set has 2 elements, it has only one subset. So we could try by putting like this minus 1 over 2, and that equals 1. And a set with 2 elements only has one subset that also has 2 elements, and that would just be itself. So we'd write that down here. A set with 2 elements has only one subset with 2 elements. And that would be itself. So that like proves our base case kind of. So then our inductive hypothesis would just be assume for an arbitrary int n equals k, where k is greater than or equal to 2, that a set with k elements has exactly k minus 1 over 2 subsets with 2 elements. And then our inductive step would just be prove for n equals k plus 1 that a set with k plus 1 elements has exactly k plus 1 times k over 2 subsets with 2 elements. Okay, so for this one, we're going to like define a set that has k plus 1 elements. So we'll say let set A be a set with k plus 1 elements. And we'll define another set. Let set B be a set that is equal to A minus A, where A is an element of A. So now B is a set with k elements. B is a set with k elements. So now A, all the subsets of size 2 either contain this element A or they don't. And all of the sets that don't contain the element A are also subsets of B. And B has k elements, so we can use our inductive hypothesis to define how many subsets with 2 elements that B has. So we can write subsets of B with 2 elements. That is equal to, or I should say number of k minus 1 over 2. And that would be using inductive hypothesis. So now, all the other subsets of A that contain the element A will contain A and then another element. So there's only k element, like k subsets that like fall under that. So the total number of subsets in A with 2, or I guess you say of A with 2 elements equals k minus 1 over 2 plus k. And then after that we can just like turn this into k times k plus 1. We'll start with k minus 1 plus 2k over 2. And then we'll like distribute this. So we'll get k squared minus k plus 2k over 2. And that is equal to k squared plus k over 2. And then that's equal to k times k plus 1 over 2. And that's it. That's all you have to do. Any questions? I know this one is kind of confusing. Yes.
So, the whole setup of the sets, what exactly are we doing there again?
Like, why did we define set A and B?
Yes.
We did this so we'd have something that we could like mess around with. If we didn't have any like arbitrary examples, it would be like very difficult to like try to prove that this set of with k plus 1 elements equals this, or has this many subsets with 2 elements. So we just defined a random set that's arbitrary. I guess this should be an arbitrary. And then we defined B as a set with the like with a minus 1 element. So these two sets are like kind of related. Related to A, kinda. So now we can use B with our hypothesis up here. So that would be this part of the equation. And then we just have to define how many sets are left over from A. Like all of this is defined a way to quantify the number of subsets in A in a way that we can eventually prove is equal to this. So once we got this half of like all the subsets in A, or this part, I guess, all that's left is the subsets of A that contain this element that we took out from B. And that would be just A with every other element in the set. And since there's k plus 1 elements in A, there's k elements that can be in a subset that contains A. So that would be like k other elements. And then A. That would be like the subsets we would be talking about. So that's how we get this plus k here. And then we just solve it out. But the whole reason we define these sets is that we'd have something we can do here, basically.
So A would be contained in the set A.
Yes, this little a is in the big set A,
In the big set.
but it's not in B. And that's how we got B. It has k elements.
Okay, so A is the plus 1.
Yeah. Any other questions? Okay. We'll move on to the next section. This one's counting. So this question is show that among any group of 5 integers that don't have to be consecutive, there are at least two that have the same remainder when divided by 4. So basically, at least 2 that are equivalent mod 4. This one is like the pigeonhole principle, and I'm not sure how much, I don't remember Professor Guha going over it super in depth, but it's basically if, let's say we let the group of 5 integers be, sorry, let the group be A1, A2, A3, A4, and A5. And then we also let A1 mod 4 equals 0. We can let A2 mod 4 equal 1. A3 mod 4 equal 2. And A4 mod 4 equal 3. So since there's only 4 like options when you mod by 4, A5 mod 4 must be either 0, 1, 2, or 3. So basically the pigeonhole principle is even if all of these are not equal mod 4, A5 must be equal to one of them. Whoa. A5 must be equivalent to another number mod 4. Woo. So basically that's all we have to say for that. Let me check to make sure. But yeah, that's basically all we have to do for this type of question. Another question that you might get related to the pigeonhole principle is if like how many integers would you need to include in a group to get where at least 2 are equal or equivalent mod 4, and that would just be 5 for the same reason. Like, it's basically how many can we go before we get an overlap. So that's all we need to like really say for this problem. Any questions? Yes.
So it should be just one more than the model?
Basically, yeah. This is the same thing as like the birthday principle. Like how many people do you need to have in a room before at least 2 of them or at least 3 of them have the same birth month? And that would be like, you could illustrate like if person 1 birthday was in January, then you went all the way through all the months. And once you get to like the 13th person, their birthday has to be in one of the other 12 months. So that could be another question you could get. And if it was 2, then you would like go through it all again and you would get to like 25, and that's how many people would have to have. But yeah. Any other questions? This one's not that hard, I don't think. Just like basically the pigeonhole principle, I think, is like kind of a fun one, actually. I don't know. Let's move on to the next one. So this one had 4 parts. So we have the string A, B, C, D, E, F, G. And we want to know how many strings or how many permutations of this string contain the substring. That was awful. The substring C, F, G, A. So for this one, we would just make C, F, G, A like its own like group, and then we would write out the remaining letters. So we had C, F, G, A. So we have B, D, E, right? And they'd be their own groups. And then these can go anywhere in this string just as long as they're like represented. So there's 4 like new letters. So our answer would be 4 factorial. Any questions? Yes.
So that's the string not mixed up in any manner.
What? Sorry.
As in, like, if the letters are C, F, G, A, but A, G, F, C.
No. Since it's a substring, it has to contain these letters in this order with no gaps in between. If it had asked for like the subsequence, then there could be gaps in between, and that would make this problem like more complicated. But since it's just substring, it would just be like this group has to be present together. And like this one could be over here or whatever. These all can be anywhere that's not in between these. So this is all it is. The next one is these strings A, B, C, and D, E, F, and D, E, sorry. Yeah. So we would do the same thing, A, B, C, D, E, and we would be left with just F and G. So this one also has 4 new like letters kind of, so this one would also be 4 factorial. Does anyone have questions about this one? Nope. Okay, cool. The next one is the strings A, B, C, and C, D, E. This one is basically, you have A, B, C, and then like, this is 1, but like C, D, E also has to be like this. So it's basically like a bigger substring of A, B, C, D, E. Like that, because they overlap. So it all has to be like this exactly. And then we'd be left with F and G. So this would be 3 factorial. Any questions about this one? Okay. And the last one is the strings C, B, A, and B, E, D. So this one, these 2 strings can't both exist at the same time because we have B, A, and then B, E. So the answer to this one is 0 because there's no strings or no permutations of these letters where both of these substrings exist. Any questions about that one? Okay. I will move on to the next problem. Here. Okay. So this one is how many strings of length 10 over the alphabet A, B, C, D have exactly 3 A's or exactly 4 B's. So this question has like 3 parts basically that we have to calculate. So we'll start with all the strings that have exactly 3 A's. And that would be, we would start with, we know there has to be 3 A's. So we'll start with where they are in the string. So the placement of A's. And that would be out of 10 spots, we have to choose 3 for each A to go. And then all other spots on the string have 3 options. So they could either be B, C, or D. They can't be A because then that wouldn't fall into our exactly 3 A's. So 3 options. So that would be 3 to the 7th. Yeah, all 7. Because once we have these 3, we have 7 left. And there's 3 options, so it's 3 to the 7th. So in total, we have 10 to the 3rd times 3 to the 7th. And we multiply them because each different group of 3 A's that we choose, there'll be also 7 options for each of them. And then we'll do exactly 4 B's. And it's kind of the same thing where we have the placement of the B's. That would be 10, choose 4. And then the other 6 spots. That would be 3 to the 6th. So in total, we'll have 10 to the 4th times 3 to 6. And now our third part would be strings that have both. So both 3 A's and 4 B's. So that would be placement of A's, which would be 10, choose 3. Then placement of B's, which would be 7, choose 4, because once we place the A's, those 3 spots, we can't place any B's. So 10 minus 3 is 7. And then the other 3 spots now have 2 options. So that would be 2 to the 3rd. So this one would be 10 to the 3rd times, or 10 choose 3rd, sorry. 10 choose 4 times 2 to the 3rd. So now that we have each part, we'll have to add these 2 and then subtract this one. Yes, thank you. So in total, 10 choose 3 times 3 to the 7th plus 10 choose 4 times 3 to the 6th minus 10 choose 3. 1 second. Okay. 7 choose 4, and then 2 to the 3rd. So we had to add these 2 together, and then we had to subtract these 2, or this one, because some of these permutations with 3 A's could also have 4 B's, and these ones with 4 B's could also have 3 A's. So they get double counted when we add these 2 together. So then we just subtract when they have both. Does that make sense? Any questions? Okay. I also move on to the last counting problem, right? Okay. And this one's the weirdest one, I think. So there's a person standing on a grid, and they can only move 1 unit of the time, up or right. So they start at 0, 0, and want to end at 20, 27, 14. And then how many ways? How many ways can they reach it? So to start with, we will just add 27, oh, sorry. Add 27 plus 14 to find the total number of spaces we need to move. And that would be 41. And then basically we just have to decide where he's going to move up versus where he's going to move right. So this one would be 41, choose 14. We could do 41, choose 27, but it doesn't matter. So I'll just pick 14. Yeah. Any questions about this one? This one's pretty straightforward. If not, I'll move on to the next part. So the next part is, oh yes.
Would it not be 41, choose 14 plus the remainder, choose 27?
Well, there's only 2 options he can move. So out of the 41 options, all we're basically saying is this, is which ones is he going to move up versus right. So like the remainder or whatever, that would, like, anytime he doesn't choose to move up, he's just going to move right by default. So the only like different number of paths are like the ones where he, times he chooses to move up. Does that make sense? Okay. So the second part, he has obstacles at 3, 5, and 17, 7. So he can't go to either of these spaces. For these like grid problems, I kind of like to draw it out, basically, like really loosely. X, Y, 27, 14. And then 3, 5, 5. And 17, 7. This is not to scale, by the way, but it works for our purposes. So basically, he can't choose any paths that go in and out of these spaces. So if we were to highlight in yellow all the paths he can't take that pass through 3, 5, they would look like this. And if we were going to do blue, all the paths from that go through 7, 17 would look like this. So kind of like the previous problem, we have like some double, like some areas in between, which would get like double removed when we like calculate this out. So we'll have to add like these middle spaces back in. So we'll start with the total number of paths, 41, 14, and we'll subtract paths through 3, 5, and then we'll also subtract paths through 17, 7. But then we'll add back in paths through both 3, 5, and 17, 7. So we'll start by calculating how many paths go through 3, 5. And that would be like, we'll have 3 plus 5 equal 8. And then we'll end up with 8 choose 5 or 8 choose 3. But I'm going to have them choose when to go up every time, just for fun. And then those are the paths that lead up to 5-3, and all the paths that go from 5-3 to the end, that would be 14 minus 5 plus 27 minus 3, so that would be 9 plus, 9 plus 24 equals 33, and then we'll choose 9, 33, choose 9. So in total, we would end up with, and this is 3, 5, end up with 8, choose 5, and then 33, choose 9. So now we'll do the 7, 17 paths. So 17, 7, 17 plus 7 equals 24. So then we'll have 24, choose 7, and then the ones from this point to here, that would be 27 minus 17 plus 14 minus 7. So 10 plus 7 equals 17, and 17, choose 7. So this one would be 24, choose 7, times 17, choose 7. And then the paths that go through both, that would be, we'll start with the same thing here, 8, choose 5. And then we'll need to calculate how many go from here to this point, and that would be 17 minus 3 plus 7 minus 5 equals 14 plus 2 equals 16, and we'll choose 2, so that would be 16, choose 2, and then we already calculated from 17 to the end, that is 17, choose 7. So this one would be 8, choose 5 times 16, choose 2 times 17, choose 7. So our total for B would be, let's see, 8, choose 5 times 33, choose 9, plus 24, choose 7, times 17, choose 7, minus 8, choose 5, times 16, choose 2, times 17, choose 7. Any questions about this part? Nope. Yeah. This one's pretty long. Is that good? Okay. I'll also post all of this online after the review. The answers? I can just post them to my SI WordPress. That is ucfsi.wordpress.com. Right here. And then you would like hover over CECS, and I'm down here, Intro to Discrete Structures. So this is my page. I didn't post my review packet, probably should have, but I posted that on the regular Study Union WordPress. But here's mine, and I'll post them both right here or something. But yeah. Any other questions? Yes.
If you finish this, are you putting the rest of the answers in?
Mm-hmm. Yeah. Since we're almost out of time, we'll do the last one. Okay. You guys ready for the last part then? Or cool. Part C is now there's a space at 10:6 where if the person visits that space, they can go to any other space afterwards. So that one is basically, it gets really messy if I use the colors, so I won't. But if I have X and Y, 17, 27, right? Or sorry, this should be 14. They want to get here. They can't touch 3, 5. Or 17, 7. But if they go to the space at 10:6, they can now go to this space or any other space. So they still can't go to these spaces, but if they go here, then they can go anywhere. I'll make it, oh, sorry. I'll make it pink, or yay, if we go here. So basically we can use the same answer from before. So I'll write that down here. 8 choose 5, 33 choose 9, plus 24, 7, 17, 7, minus 8 choose 5, 16 choose 2, 17, 7. So now all we have to do is we have to add in the situation where he visits this space while still avoiding these spaces, and then goes through 17, 7. Because like anything else outside of that range is already accounted for basically. So all we have to worry about is going through 10, 6. So we'll start with the total paths to 10, 6. Sorry, paths to 10, 6. And that would be 10 plus 16. Oh, sorry, 6 equals 16. And we'll choose 6. So 16, choose 6. Then we'll do paths that pass through 3, 5. And that would be 8, choose 5 again, like to get up to this point. And then we'll have, 6 minus 5 plus 10 minus 3 equals 1 plus 7 equals 8. Then we'll have 8 choose 1, which is just 8 by the way, but we'll keep it like this to make it consistent. And then after that we do the paths from 10, 6 through 17, 7 to the end. I'll just write end. And that would be 7 minus 6 plus 17 minus 10 equals 1 plus 7 equals 8. And then 8 choose 1 again. So these are paths from 10, 6 to 17, 7. 8 choose 1. And then that would be multiplied by this group again, which we already figured out up here, 17 choose 7. So that times 17, 7. So now, like, all of these paths right here would be 16, choose 6, minus 8, choose 5, times 8, choose 1. And that times this. So 8, choose 1, times 17, choose 7. So now what we have to do is we have to take this answer up here from part B and then add in this bunch right here. So I'm going to copy and paste it. B. Paste. Plus 16, choose 6, minus 8, 5, 8, 1. And this would be our final answer for part C. Okay, any questions? Okay, we're almost out of time. Does anyone have any, like, just, I guess, other questions? I don't think we can do any, like, much more from the packet. But yeah. Yes. Uh-huh. Okay.